Okay, so we're gonna get started. So this is room 225A, and this is the mining and exploration operational enhancement pushing forward session. And if you are in the wrong place, don't worry, like you can stay. I think you will enjoy these presentations that we are going to have here today. So I'll get started with the first presentation. We have Matthew Deutsch. Deutsch. Yeah, so Matthew Deutsch is a mining engineer with Maptech, North America, and a PhD student at the Colorado School of Mines. Matthew's work and research focuses on helping mine engineers and geologists make better decisions. Matthew primarily works on problems in an open pit optimization, open pit design, geostatistics, and grade control. Will, welcome.
Thank you. All right, thank you. Thank you guys for coming. I know last session of the last day, at least I'm not the last talk, sorry, whoever that is. But no, it is, but I do appreciate you coming today. We're going to talk about the ultimate pit problem, which is kind of an old, maybe out of fashion problem a little bit. But sometimes people think that they can get around it and they don't need to use it. And if you have software that's capable of doing that, then by all means. But a lot of the time, we still use what's calculated from an ultimate pit style of analysis. And if you're not familiar with it, I'll remind us all. So, but really what I want to talk about is the addition of these operational constraints of mining width, of a minimum mining width at the bottom of the pit. And I feel like this is an important tool that we've been lacking. So we'll talk about block models and mining widths. We'll talk about the grade control problem, which kind of led to this problem just very briefly, and then we'll be right into ultimate pits and how we can solve this problem effectively. So as we know, open pit optimization is done with these block models, sugar cube kind of styles of blocks. And the size of those blocks is actually kind of difficult. It's tricky for people to decide. Maybe the height is easy, just the bench height. But the different sizes, people have different feelings about what the sizes should be, and it's used for many different purposes. This block model is passed around to a lot of different people for different analyses. Your geostatistician might want something different than your engineer, and so this block stuff gets a little tricky. When we talk about this, we sometimes talk about selective mining units, but that's kind of silly, right? It's not, you're never actually mining an individual block at the bottom of a pit, for example. But if you're using an optimization technique like a ultimate pit analysis, it's going to mine down to an individual block, no question. So what we want to do is we want to make our tools, our optimization procedures respect the operational reality, which is we want pits that look good. We want pits that we can mine. We don't want, what just the computer is going to spit out at us right away. And this is what motivates us to consider mining width as a separate thing. So what do I mean by mining width? Well, I'm talking about mining widths in our context as small collections of blocks. So not just one block, but some grouping of blocks. That's what we're actually going to be able to design. We're going to be able to put a ramp down to it and put a shovel in it and operate in that area, not an individual block. Because our blocks are going to be smaller to represent geologic variability and that sort of thing. So I'm talking about some kind of collection of blocks. And sometimes that's called a structuring element in different fields. And for now, we're just going to call it a mining width. So the first problem that really brought this to my attention and was something that I really wanted to kind of tackle is this grade control problem. And that's when you are trying to decide where to send material. So I don't know if the mouse works. It does. Okay, good. So this is a plan view bench of a real gold mine. And these blocks here that are green are supposed to go to the mill, and the blue blocks to the leach, and the red blocks to the dump, right? So that's what we would like to do, and that's based on the economic information. That's based on the grade that we estimate is there. But the problem is, if you were to give this sort of model to, you know, a surveyor and say, stake that in the field, or to an operator and say, dig that with a shovel, well, that's ridiculous. There's no way that this individual block here that we say is supposed to go to the leach is actually going to go to the leach. It's going to go to the mill because it's surrounded by blocks going to the mill. You know, we're not mining with teaspoons. We're not mining with helicopters. You know, we're mining large areas with large equipment typically. So we want to reclassify blocks. We want to change it. So we're going to change this block to go to the leach and so on. We're going to make that reclassification, and that's an operational requirement. That's based on that we need to do this so that we're able to actually mine the deposit. And then, of course, we also need to turn it into nice polygons and so on. So this problem is captured, and I'd be happy to talk about this with anyone. It's in a product that Maptech offers called the Grade Control Optimizer. But that's not exactly what we're here to talk about. We're going to talk about the ultimate pit problem instead. So what do I mean by the ultimate pit problem? So this is when we're trying to decide, or we're asking ourselves, we're going to mine this, and we're going to leave this behind. And so it's a selection problem. It's a question of, we're going to mine, you know, what's in this pit here, and we're going to leave this stuff behind. And the point is that the stuff that we're leaving behind doesn't have the value to support the mining operation. So it's a decision that we're making. This is still used. You know, typically people focus on deciding when they're going to mine things, like a block scheduling problem, like I'm going to mine this, and then this, and then this. But this kind of base high level, I'm going to mine that and leave that behind, is still useful in practice for determining, you know, infrastructure placement, equipment sizing. It's part of that whole circular process of designing an open pit mine. Historically solved with lovely Lurks and Grossman algorithm, and now it's typically solved with pseudoflow or push relabel. But we want to add mining with. So this is our problem really in a picture, where we would like to make pits that look better, essentially, and that are more operational, but we don't want to sacrifice too much value when we do that. So your typical ultimate pit will go down and say, this is a cross-section now. It'll say, let's go down to this individual block, or we're going to leave this block behind, or we're going to make those kind of minute choices that the ultimate pit optimization is allowed to make. But really, that's not exactly what we would like our computed pit to look like. You know, you're not going to mine down to an individual block. We'd prefer these much nicer, you know, big flat bottoms and so on, right? And so then how is that typically done? How do people typically do this? Well, they calculate the ultimate pit, and then they'll just chop off the bottom, right? They'll just chop off the bottom when you're designing your pit at the end. You know, you'll go down to some benches and you'll say, oh, it's too small. I'm going to go up a couple benches and start digitizing my pit starting here. That's kind of, you know, think about that for a little while. It's a little silly, right? Those blocks at the bottom that the optimization said to mine are exactly the positive blocks that are supporting the pit in the first place. Those are exactly the blocks you don't want to lose. But what people do is they just chop them off because we can't fit down there, right? It's just crazy, right? But the alternative is trying to expand the bottom, and that's tricky because when you expand the bottom of an open pit mine, I mean, that gets projected up at an angle. You're taking tons and millions of tons possibly more waste, and that's much harder. So that question about do we chop, do we expand, how do we do that appropriately? And that's what we're trying to address here. Some people will try and tackle this by reblocking. So taking blocks and combining them into bigger blocks and then doing your optimization on that. And saying that, yeah, okay, I can take this big block, so I don't have this going down to little blocks because my blocks are bigger. The problem with this is it can be hard to represent precedences. It can be hard to represent your slopes. There's also a question of where do you start the reblocking? Like, do you start it, you know, on this block, or do you start it on this block, or this block? I mean, it gets tricky. It's not an ideal way of solving this problem. Reblocking is not ideal. Another option comes from image processing, and it's this technique of mathematical morphology, which actually comes from George Mathron and Sarah. And Mathron did so much stuff, and he did this too. Crazy. But some of this it's a geometric technique. So it doesn't look at value, but we still change our blocks. So we're going to be, this is face-looking pit from an actual ultimate pit results, it's saying, okay, we're going to leave these blocks behind. We're going to mine these blocks here. That's what the dark green is what we mine. If we perform these mathematical morphology operations, we're going to add in these lighter blocks. It might be kind of hard to tell, but at least kind of squint and see this is bigger, right? More blocks are being mined. We've added more blocks to our problem by applying this closing operation. We can also apply the opposite, which is this opening operation. And what it does is it makes things smaller, so it gets rid of these pieces that don't satisfy the mining width. It throws them out, right, and changes it into something a little bit, hopefully, more reasonable. So why don't we apply them both at the same time? And we kind of, but the whole point of these things is that this is not ideal either. And why? Well, it doesn't look at value. It doesn't look at the dollars. It doesn't look at, whether this is a good choice from the perspective of I want to make the most, economically feasible pit. This is just, turning blocks on and off without looking at the value at all and saying, I'm going to mine this, I'm going to leave it behind. That's no good either. Another thing that people have tried is, the floating cone algorithm, if you're not familiar, starts with a cone and kind of scans it over the block model and says, we're going to mine this, and it makes sense. And it's a heuristic technique. It's completely fallen out of favor, right? It was only appropriate when your computers were not capable of solving the actual problem. But it actually lends itself very well to this problem. Let's say, we'll just make it a fat cone, right? It'll have a bottom, and then we'll float him around and make those choices. And I'm not going to go through the examples in detail, but the point is that it doesn't, it's still a heuristic, and it still suffers from the exact same problems that floating cone did in the first place. So that's out too. Can't do that. Shouldn't do that, rather. I mean, you can do anything. I'm not going to tell you. Our point, though, here is that we want to optimize this. We want to make the best decision, and we want this tool, the ultimate pit calculation, to remain a useful tool. It's not going to give you the actual final outline, right? I mean, nobody uses the actual ultimate pit that they calculate 20 years before they start mining or whatever it is as the final outline, but it's still a tool that we use during the process, and improving that in the early stages and improving that tool is important. And why we want to turn to an actual mathematical style of optimization is that it opens up possibilities. I'm going to come around here. I think I'm yelling loud enough you can hear me anyway. This is what the ultimate pit would tell you. It says mine just these blocks, right, down to get this one. If we expand it, we say we have to consider a mining width. We're going to expand out or we're going to chop off. The point is that if you do this optimally, if you do this correctly, it'll expand out to the left, because that's better, because it opens up this possibility here. So it actually expands more than you might expect to take advantage of the fact that maybe not take advantage, to pay off some of the problems associated with accounting for the mining width down here. If we ignore this is a 3, -1, -1, has overall a value of 1. We don't take it in the ultimate pit because it doesn't make sense. But when we expand for a mining width, okay, then I'll take it, and it does make sense. This is a really small synthetic example, right? But it happens in 3D cases a lot, where if you are doing it manually, expanding or chopping or whatever, you're going to miss this stuff. You're never going to find this value that you could have used. So yeah, that's part of our reason, why are we doing this? So what the research is focused on so far, and what we've done is we've come up with the formula. I wouldn't be, a good CSM student if I didn't put a bunch of math on the slide. It wouldn't be appropriate. We're not going to go through it in detail, but we'll come up with this new idea, this new formulation for handling that mining width constraint. We do have some choices, though. I said I wasn't going to dwell on it, and I didn't. Thank you. Okay, all right, good. We do have some choices, though, about saying, okay, what constitutes something not satisfying a mining width? So these are plan view cross-sections now. And we're saying, these blocks down here don't satisfy, oh my goodness. These blocks down here don't satisfy our mining width because they're too small down to an individual block. That's not appropriate. We could also say that a block satisfies a mining width if a block below it satisfies a mining width. And this is kind of, I don't know, not super interesting, but it is a choice that we need to think about. I'm not going to spend too much time on it, though. Let's get to some funner stuff. The point is that what we've done, though, is we've made our problem awful. We've made it just so much harder by adding in this mining with constraint. We've made it not very nice. The ultimate pit problem, we love it because it's so simple, so straightforward, so perfect. We just throw these like super heavily optimized solvers at it and we get out the right answer and everyone's, happy, right? But by adding a mining width, we have made it so that that's not okay anymore. It's no longer a really nice problem. It's a really mean problem. And here's an example of where it's mean. So what we like to do is we like to make our problems linear, which is a term that makes them like basically fast to solve. But if this is another plan view section, and it's saying, okay, I need to take at least 4 blocks. I can't take, 1 block at a time. And let's say these are the values. So if I take just this upper square, I got 30 minus 22, 8, right? So by just taking this, and it's symmetric, so the same. If I take everything, I got, 16, right? But if you just throw this at the computer and you say, okay, this is a linear kind of problem, let's solve it, it's going to come back and say, oh, thank you. It's going to come back and say, okay, how about I mine that middle block, and how about I mine 1/4 of these other blocks? It's like, well, that's not okay. We don't want to mine partial pieces of blocks, but that's what the computer is going to tell you to do. So that's the problem. We lose some of the beauty of the ultimate pit problem. But the formulation, it could be nice again. So here's our formulation, and how could we make it nice? Right? How could we make this useful? Well, we could just cover up this is the mining with part, just cover it up. Of course, it's being projected on my hand, so I can't cover it very well. But if we could just hide that, we'd be back to having a nice problem again. So here, okay, all right, I'll cover it up with this square. Right? We cover up the mining width part. But then we're kind of back to the beginning, right? We just said, okay, yeah, let's put our dirty dishes under the bed and I don't know, forget about them. That's not going to be ideal. So we need to turn to a technique that's going to not just cover it up, but maybe move it somewhere else. And that's what motivates us to consider decomposition. And decomposition is just a fancy word for saying I'm going to split the problem in pieces. So I'm going to split the problem into 2 pieces. The first piece is going to do mining widths. We don't need whatever. And the second piece is going to be our ultimate pit problem again. And we're back to being happy in the sense that we've taken our problem, we've taken the mining width aspect of it, lifted it out of the problem, and we're left with having to solve a bunch of ultimate pits. Let's do an example in just a second here. So we want to split our problem into pieces. One of them is going to stay nice. That's going to be our ultimate pit problem. And the other is going to deal with everything else. It's going to tell us how to deal with everything else because it will have those mining width constraints in it, and it will give us this notion of how bad, how good it would be if we could satisfy that mining width constraint, and then we can use that to modify our values. There's another technique, and that's this BZ decomposition, which you might have heard of. And it has this additional step of orthogonalizing, which is another fancy word, but it actually splits the pit, not just the problem. So lots of splitting going on. Let's do an example because it's too weird right now. So let's say this was our block model, and yeah, we'll read out all the numbers. No, the point is this is our block model that we would like to solve with a mining width of 2 blocks. If we solve for the ultimate pit, we're going to get that little gray pit in the middle. That would be our best, that's the ultimate pit. But it doesn't satisfy our 2-block mining width. So we go to our master problem and we say, hey, that mining width thing, are we okay? And he's like, no, you don't satisfy the mining width. You need to move some of that value around. We need to find out, you're not satisfying the mining width specifically down here. So what I'm going to tell you to do, and the master problem tells us this, is it says, take some value from this 9 and give it to its neighbors. And that value actually comes from solving a little small problem. And it says, okay, fine, all right, you've modified our value, and we give some of that 9, and we give it to its friends, and we solve for a new pit. Okay, but then we take this one, and we put it back and mix it in with the others, and this is that orthogonalization step, where we turn it into these 4 different pits, that I call them ortho pits, because they're orthogonal pits. Not this isn't much of a pit, is it? It's just one block, but regardless. So we saw, and then we say, okay, can you come up with something that satisfies the mining with here? And it says, well, sure, I could take this, 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 and this, and I would satisfy the mining with. But that's not the best I can do. Why don't we take some value and we shuffle it around a bit further? We move some of the value instead of over here, we move some of it over here instead, right? And so we're trying to make that decision, and we solve for another pit. So you can imagine if you were like a software pack, you'd be solving for this, a full pseudo-flow, full ultimate pit every iteration, right? You're just moving that value around. And we get these new ones, and then, okay, fine, right? We combine them back, and we end up with the pit that is both of these together. And that is the right answer. That is the best answer that we could do. So we had to solve our ultimate pit problem like 3 or 4 times in this case, instead of just once. And we had to do that work before that I talked about moving the value around a little bit. And there's some tricky details in there. But it's not that bad, right? It's much, oh, I'm going over time. It's much better than, you know, it's not too bad, we'll say that. So what we want to do is extend this to the block scheduling problem, of course. I think that's important. Instead of just mining, you know, for an ultimate pit, we need to satisfy a mining width for a sequence. And we feel like that is important. So manual methods are out. Don't just remove the good blocks, you know they're good. Reblocking's out, geometric methods out. We need to look at these promising techniques to solve this problem efficiently. So it's still very much used today, and if we can get that minimum mining width constraint in there for a low computational cost, doesn't take you that much longer, it'll be just that much more useful. So there we go. It's in progress. It's a progress talk. I'm done. Thank you, guys.
Is there any questions for Mark?
Matthew,
Matt? Okay.
close.
Okay. Close enough.
Gospel.
You
Yeah.
gotta have one. When will it be?
Oh, you want it? That's what that question implies.
Only for the last 35 years.
Only for the last 35, you know, see, that's perfect.
And the last 3 PhD students or so.
When? What a good question. It'll be done this year. This part will be done. Absolutely, no question. And, I mean, I'd love to talk to you more about getting it in your hands then as well. Because it is research and we want people using it and we want to try it on big stuff. So that'd be great.
There's no more questions, right? So,
Okay.
okay. Well, thank you. Okay, so our next presenter is Ismail Traore. So Ismail, he works for Barrick Gold in the Kibali mine in the Democratic Republic of Congo. He's currently the technical services manager at the Kibali Gold Mine, and he's responsible for the management of various technical departments of the Kibali Gold Mines, including mine planning, geotechnical engineering, drill and blast engineering, mine survey, mine ventilation, hydrology, page filling, and cost control. In his early career, Ismail worked as a production engineer with the ENG aggregate quarry in Algeria prior to joining Colorado School of Mines, where he worked on various research-funded projects. He also worked at Lolo Gold Mine in Mali, where he held numerous technical production and project management roles before assuming the role of technical services manager in 2016 at the Kibali Gold Mine in the Democratic Republic of Congo. Ismail earned his Master's of Science degree in Mining and Earth System Engineering from the Colorado School of Mines and his Diploma of Higher Study in Management from the Institute of Management and Computer Science in Algeria. He also has a Master's degree in Public and Private Law, Specialty Business Law from Perpignan University in France. So welcome to Ismail.
All right, thanks, Alberto. Just need to project it here. All right, so moving away from open pit, so let's do some underground mining here. So that's much more exciting, right? All right, in my today presentation, I'll be taking through one of the hot topic that we have been having in underground mining environment, which is the determination of a long-hole open stopping mining method sub-level height. So in my presentation, I'll be taking you through three main points. The first one would be the problem that we currently have in the mining industry, and then how various people are addressing and how various people are looking at that problem. So followed by an approach that we come up with based on the work that we've been doing over the past years. So that approach is really an integrated approach. So you holistically have to look at that problem by doing iterative and comparative analysis for defining the sub-level spacing. So there, we look at the problem in two different approaches. The first one, we look at 8 critical points that are all important for defining the sub-level spacing. The first step would be looking at high-level analysis to get your head around the problem that you're trying to solve by looking at the level spacing option that you're intending to assess. And also, usually you do a higher level strength, weakness, opportunity, threat analysis, which is a SWOT analysis. And the mining method are usually reviewed as well and cash flow analyzed. So the last portion, which are the last 3 main points, that's when you take a closer look at the problem by doing a detailed geological assessment, geotechnical design assessment, and then the stopping design, looking at the drill and blast aspect. And then lastly, you look at the life of mine plan itself. So just this problem, as I said, it seemed to be a simple problem, but it's not really. It's really a complex problem that we have here. So usually it's easier to say that when you increase the sub-level spacing, so it's decrease your development rate, therefore you can access to your stock much quicker. So that's a common sense, right? But the problem is really how do we define the optimum sub-level spacing? So you can put 10 engineers in the room, everybody would come up with his own reason for why exactly he's thinking which number should be correct. So that's what we're here today to present on the approach how we can solve it. So some people might think that the very conservative engineer can say that you need a smaller level spacing. You choose 15, 20, 35, whatever, depending on the deposit. Or some engineer might say that you have to go with higher level spacing, 50, 40, 70, 100, whatever that number might be. It's obvious, the first option, you don't have to do more development, but the first option, you do more development, but the second option, we do less development. But the problem is still which option is correct. So this problem is such complex that if you do not adequately define it, you end up having major geotechnical issue, you end up higher dilution, or losses, and many other consequences that can negatively impact the value of the overall project. So today what I will present it is like an holistic approach that, as I said earlier, for defining the sub-level spacing. So this is the approach that we're looking at, as I said earlier. So this is iterative and comparative approach that you use for defining the sub-level spacing. First of all, you do a SWOT analysis of various level spacing. So you kind of have to look at what are the options you really want to look at. based on the equipment that you have in place, based on higher level understanding of the geotech of the mine site, and then some other operational constraint. So followed by you look at the mining method review. By reducing or increasing the sublevel spacing, do you need to change the mining method, yes or not? And also you have to do higher level cash flow analysis to have a good economic guidance before you move forward with the problem. So on the next step, that's when you start having to do a detailed assessment of the problem that you have. The geology is a king. So you always have to have a better understanding of the geology. So you have to assess the geology first, from confidence level perspective or from understanding of the geology as well. The geotech is very important in underground environment, especially when you're dealing with voids. Increasing the sublevel spacing mean that you're making bigger void. So you have to look at that. You have to do a detailed assessment on that. And then when you move on from geology and then geotechnical assessment, which are very critical, you move more into the operation side of it, where you have to look at the drill and blast engineering, how you're going to be drilling the stope, how you're going to be firing it, how you're going to be charging, and all those sort of other aspects of the operation. So when you do all of those assessment, so you're ready to go. You can start designing those scenarios that you firm up. So usually we try to reduce the number into two. We have to group it, and then we reduce it down into two. And then from there, you have to do your capital development design, and then higher level your operational development design as well. So after doing that, we look at the scheduling. So we have to optimize, or we have to use a production optimization tool to assess our production schedule, to assess the life of mine plan. What is the benefit of option A against option B? And after doing all of that, lastly, you need to look at the operation and the risk assessment of each option. Why do you think option A is better compared to option B? And then it's only after that you can come up with a optimum or the correct, adequate sublevel spacing. So here in this specific case, after going some other background work, we were looking at two main options in this specific mine. The first option was the sublevel spacing to be 35-meter high sublevel spacing. You can see the design. There is no big change. Ideally, we're looking at this area. It's not the full mine. So in this specific study, we're looking at this area of the mine because of the geology and some other aspects. And this is the second option. So we have a 50-meter level spacing. As you can notice, we have less level, the first option compared to the second option. As I said earlier, usually you do higher level SWOT analysis by looking at it just on high level. You can see clearly when you look at your inventory that, the 50-meter level spacing would result in lower meter development and also lower resource requirement. And then you have some other advantages from paste filling because you reduce the number of derived activity that you have to deal with. And weaknesses, again, this is kind of higher level review. Usually we have issue with, as the stope gets higher, you end up having some other issue with charging operation, the retention of explosive and some other stuff. And also the geotech is a critical one. The biggest threat that usually when you increase, you have to make sure that you have a good geological understanding. Geology is very important. So there is no going backward if you start developing, your mine with higher sublevel spacing. You're already there. It's done. So you have to make sure that you have a good understanding of geology. Geology is really usually the tipping point when you want to look at this problem. And you have opportunity. The opportunity as you start your production earlier because you don't have to do so much development, and then you save some costs, and then some other capital and sustaining capex opportunity that you have. This is just usually high level to kind of, give you a brief idea on where you really need to look into when you have to do that detailed assessment in the next section that I'll be talking through. So as I said, mining method is very important as well. So by reducing or increasing your sublevel spacing, do you require to change your mining method, yes or no? In this specific case, that was not required. The mining method that was being considered is sublevel open stopping. That's transverse, that's in primary, secondary fashion. So the stopping sequence, as you could see by following the number for the 50-meter level spacing, which is the second option. So you have to mine 1 and 2, primaries, and then paste fill them before you can get the top one. But so when it's a 35-meter level spacing, you could mine up to 3 different lifts. So you could see you have a bit of advantage of 5 meters there. You cannot mine the secondary stop. You mine the secondary stop only after paste filling the primary stop. And also for various other reasons, the paste filling constraint, the UCS requirement, and some other stuff. So with a 50-meter level spacing, you could mine only 1 stop at the time for the secondary. This is just having a look quickly, the cash flow by considering the development meter requirement that is driven by the inventory that you come up with earlier, and the stopping costs, processing costs, G&A, OPEX, and then some other sustaining capital. As you could see, by increasing the sublevel spacing, the cash flow tend to be better than reducing it. However, it doesn't seem to be that significant, which is a very good, which is an important point to get our head around. The next one, as I said, briefly, just geology. We spend a lot of time usually understanding the geology, trying to understand the coverage that we have, the confidence level that we have, and then how practical is a grade control drilling in terms of having the information that you need in terms of the intersection of a drill hole to the ore body. So in this specific deposit, usually underground mining operation, when you start, depending on the deposit, obviously, sometimes you don't not have a lot of higher level of confidence because you have just those advanced drilling where you drill those from the surface before you get into your underground working and start drilling your grade control drilling. So here that was quite a bit of issue. We did not have very good coverage, which puts a big question mark in there. Is the geology going to change when you get underground and then start drilling it? Yes or no? That was a bit of unknown. And also most of the drill hole that we have was not providing a very good intersection to the ore body. So therefore, we did not really have a very good idea on the hanging wall and then the foot wall because we did not have like a good intersection of a drill hole into it. So as I said earlier, because most of the hole was either exploration hole or advanced hole, which were vertical. It's only when we get underground, you can have a much better intersection to the ore body. So there's a big question mark in these two options that was being assessed here is that we did not really have a very higher density of drilling, which is a very big question mark. Second, as I said, underground mining environment, geotech, one of the most important aspects that you have to look at in any sort of design that you come up with. So in these two options that we did evaluate empirically the geotechnical stability of a stope. As you could see, usually what we do, we look at the empirical stope stability chart. So what that one was showing us is that as you increase the level spacing, your hydraulic radius become higher, and you end up pushing your stop into the transition and caving zone compared to when you maintain it at, say, smaller level spacing of 35 meters. So that was a big one as well, because you have your stop in the transition zone, that can be managed, but when you start falling into the caving zone, you can see that you have a bit of issue. And the other one is that you have to look at the geotechnical structure. Structurally, how can we manage this structure from mining perspective in terms of avoiding massive failures, dilution, and then some other stuff. Also, how do we control the geotech? Looking at the empirical assessment, that's one thing, and the structure is the second thing. But in reality, what are the control systems that we could put in place in order to mitigate the issue that we might potentially face? So cable vaulting coverage, as we increase it, especially to 30 to 50 meters, so that's become an issue. Usually you don't have a very good coverage. The cable vaults become ineffective because you are not really pinning into the wall properly because it's much wider. It requires much wider length of cable that you have to install. Just quickly on the stopping, usually the biggest one is that when you increase your stop length, so you need to use a rest boring machine. That's a way that you could mitigate the deviation issue. Otherwise, you might not even find your hole because it ends up becoming spaghetti and stuff. But there is some few other techniques that you can come up with in terms of avoiding, in a production drilling. But the raising is still going to be challenging, which would require a rest boring machine. So you can do up and down hole drilling to reduce your hole. But in this specific rock also, we have some issue, based on various core logging. We have seen that we have issue with our foliation. So that is being, from experience really, if you look at any of the exploration hole or any production drilling hole, the hole always tend to deviate after 10, 15 meters exactly in the same direction. Imagine when you increase the level stopping, so what do you end up having? Deviation was a challenge when you have to increase the sub-level spacing. And also the other challenge is the charge-up practices. Usually you end up facing some issue in terms of retention of a product, even though you can change the density and do a few stuff around it, but that can still be an issue. And also when you start having issue with your stop, you would not have that much flexibility to fix it up. For example, if you have a bridge in your stop, or if you start losing the ore, how you're gonna come back to recover it and so on. So those were some of the issues that we identify when we're doing the production stopping design and drilling blast assessment. Just lastly, the biggest one, the life of mine plan. So at the end of the day, that's a very important point that we have to analyze and understand which mine plan is better and then which mine plan provide the filter for the business at that particular point in time. So to do that, we have used the SOT, the Enhanced Production Scheduling Optimization tool for underground. And when you look at this graph is really showing the development profile, right? So by looking at both development profiles are pretty similar really, but however, as you could see, with a 50-meter level spacing interval, you finish your development earlier compared to the 35-meter level spacing interval. So again, there you have some advantage with a 50-meter level spacing interval because you can do some saving on those 2 years, but you can still do some few stuff around to still bring that advantage in. That's a big one. I think that's what you could foresee even before running the schedule. I think that's what the schedule is showing us. So by increasing the level spacing, you have a quick access to the stop because you require less development. So therefore, if you could see here, the production rate is higher at the early stage of the project. So you get more ore early, maybe just for 1 year, and then after that, both profiles become similar. And it's the same thing for the ounces as well. And you have a higher flexibility as well, but that's just for the short term. You have a short-term benefit for the 50-meter level spacing interval. But the key is that, you know, does that short-term benefit outweigh all the other risk and then all the other issue that we have picked up when we're doing that, you know, integrated comparative things by looking at the mining method, geology, which was an issue, geotech, which was an issue as well, and drill and blast, which was challenging, even though you could get our head around that one. So the key is really in looking at the operational risk as well. So that's kind of going through that process clearly tell us, you know, we kind of concluded, but everybody knows the conclusion already by looking at all of these aspects or all of these facets of the problem. So in conclusion, the 50-meter level option provides quicker development, faster access to the stope, and improved flexibility in the early years. But the biggest problem is geology. As I said, geology is king. You have to make sure you understand your geology, otherwise you don't have a mine. So with limited amount of drilling, it's really doing the unknown, because if anything change in the footwall or the hanging wall or the geology itself, the geometry, so it's become very difficult to manage that from stope design perspective. So controlling the hanging wall and the footwall would become challenging, especially when you start doing the mining, when we have something that are not expected. And also increasing the sublevel, increase the hydraulic radius, as I said. So, and also the unsupported extent of the hanging wall. So the cable bolting become not very effective. And also you have some other risk associated with a combination of uphole and downhole. All right, thank you. That's all I got.
So anybody has any questions for Ismail?
Yep.
Ismail, why two options, 35 and 50? Why not 35, 40, 45?
Because at the end of the day, when we look at it from equipment that we have, the solo that we have. Doing 40 meter would be very ineffective operationally, because you're just gaining 5 meter extra and 10 meter extra, especially when you're doing the production drilling. That would make the cycle much longer. That's why we go 35 and then 50. Yep.
And the watering rate on the development, how fast you can drop the water?
The dewatering.
Do you have a lot of water?
We do not have that much water, so most of the water are being collected at the shaft. So what we do usually, we drill some hole so that we can drain the water, and then we collect all the water down at the shaft, and then we pump it out. So we have a very big pumping capacity at the shaft. Right.
Okay, well, thank you.
Cheers.
So we're going a little bit fast in the schedule. We have a couple minutes. So I'll introduce Klaus in a little bit.
Where can I put
You know, I'll save the presentation unless you made some changes, but we can put it in. So it's in there. Yeah.
No, no, no.
So just a follow-up
Oh,
question.
where is
It
it?
looked like from the metal produced, the first 3 years made sense from the 50 meter. But beyond that, you might as well have dropped back down to 35 meters
The problem is that that's when you have to drop your development rates ready. Because if you maintain the same development rate, so it would not make too much economic sense to just develop the top part. And the other one is that we have a mining method constraint, which is bottom up. You really need to develop all the way up to the bottom before you can start mining up. So therefore, you don't have much choice from the mining method that you have. You have to definitely develop to the bottom and then start mining up.
So anyways, I was gonna ask you, so I'm really happy you reviewed this. That's good.
Yeah,
Yeah, it's not here. Yeah, so yeah, Oh, okay. Oh, sorry. So I'll just reconfirm the Grasberg presentation on block caving is not here, so we'll start over at 3:25. Okay, so we're gonna get started. So at this time we have Javad Shahmoradi, he's a graduate student from the mining engineering at the New Mexico Institute of Mining and Technology. Thank you.
So today I'm going to present monitoring of inaccessible area in underground mine in GPS or GPS denied environment with a fully autonomous safety inspection drone. Today we are going to talk about underground mine challenges first, then we're going to talk about opportunity of utilizing drone, a spherical drone design, and the cage simulation, object detection drone, obstacle avoidance, and finally we are going to talk about the conclusion. So what are the challenges of underground mines? As you know, in underground mine, we do not have any GPS. So it's a GPS-denied environment. Like you use your phone in surface to navigate yourself to your destination, you cannot use any map or Google map to navigate your drone in underground mine. So it's the first challenge. The second is that there is no light there. You have to use your own drone light. And also it's really harsh environment, shotcrete, and it is excavated already or temporarily supported, or everything is harsh. This is a confined space. The space is designed to use by the most with the machines. And there are a lot of dust over there. They are working down there, and they produce dust. We have air velocity for ventilation that makes our drone flows back, and we have a lot of obstacles. If we want to have a better perspective of underground mine, these GIFs show you how it look like. Maybe you even expect a vampire comes out of one of these tunnels. But anyway, this is a really dangerous area. You don't know what the gases maybe are going to be there. It's not safe for people to go there, especially for abandoned mine or even for active mines. Mines always are, some of them are inflooded, and we have droplets, water from the roof, and this is a kind of not safe area for people. For the purpose to have a safe area for working, we need to monitor underground every day or by the time. But who goes and monitor this area? So people, human needs to go there and monitor for cracks, for gases, for hazards, for everything. A better idea by this day that we have advancement in drone technology and robotics, we can send our robots there. So we came to the idea of designing a drone to be able to fly in underground mines, and this would have a lot of benefits. It can fly over a flooded area in the mine. It can have remote sensing, hazardous rock and soil type detection, assessing collapsed area, volume, buried victim detection, first aid delivery, wall thickness detection, hanging wall failure detection, and rock bolt and anchor failure detection. There are a lot of more applications for these robots. As I said, underground mine is a harsh environment. So we came to the idea to protect our drone from colliding the wall. What we did, we designed a cage for our drone. These are some of the concepts that we tried on them on 3D. And finally, we came to this concept that is our final concept. Because we need to have a better vision for our sensors. These cage blocks are sensors, so we came to the combination of triangle and pentagons to have a better vision for our sensor from the pentagons. After designing the cage, we have our drone, and we installed our drone inside, connected our drone to the cage. For the cage, we did some steps to finalize it. We did finite element analysis on the cage to see how much on the displacement or on the colliding the walls does it survive or not. The analysis shows that with 5 millimeters displacement, our cage are going to survive. But we changed our material to a new material as a flexible material, and we had better results. The next step is to test our drone in the lab, and we follow the right side algorithm to finalize our work by the future. These are the tests that we do in the lab for our drone to be ready in underground mine. Another step is to detect object in underground mine. In underground mine, we need to find if someone is a worker or an object that we need to care about it. For now, you can, your phone can detect objects in surface, but for underground mine that has we have not too much light is another story. We are working on a deep learning methods to find objects. Workers are covered with the clothes and hats in underground mine. The story is different. We are still working on this part. And the other steps is to make our drone obstacle avoidance. We are going to use LiDAR sensors and ultrasonic sensor to detect the obstacles and avoid obstacles. Right now, maybe you use your sensors in your car when you drive with blind spot, or when you park your car, you use your sensors. For drone, it's the same. We use the LiDAR sensor to detect the distance between our drone and the obstacle to avoid it. But anyway, this cage is gonna protect our drone. The conclusion for the proposed drone is able to recognize the obstacle in the mines and work in the GPS-denied environment. There are benefits from a drone that can improve the safety of mine operation, and this drone is able to access unreachable area and dangerous area, and enhancing the mine rescue mission for removing trapped personnel from unsafe situation. Early detection of hazard and monitoring of hazard to reach areas, and increasing the time of a rescue mission. This is our team that we are working in New Mexico Tech on our drone. We have a team from mechanical engineering department and mineral engineering department, all of us working on this drone to finalize it and do the test in underground mine. And thank you. I'm ready for your question.
Yeah, thank you. So we have 5 minutes for questions. For sure.
You gonna show us your drone?
Yeah.
Yes.
This is our drone, finalized for this presentation. This drone, this is the cage. For the first time we used the joints that they didn't have any base. So with the drop test, we loosed our joints. So we changed the material, and now we use the flexible material for our cage. So our cage is we can squeeze it. And for the connection between the cage and the drone, we designed this ring, and there is a module to install the gas detection sensors and other sensors here under the drone. And we are going to use LiDAR sensor around the drone. Camera is going to be able to have a vision through these pentagons. Yeah. Sure.
So you're saying you want to use a LiDAR sensor on that exact platform, or is that just the concept of cage?
We are going to use LiDAR sensor for obstacle detection. For scanning underground spaces, we need a specific quality of LiDAR. So that LiDAR is going to be used in this file.
Okay.
Yeah.
How would it make difference between the cage and some other obstacles that are around? Because when your sensors start looking at most likely it's gonna see some of the metals that you have.
We use our obstacle detection sensor outside of the cage. So it's not gonna.
So how is that connected to the drone?
These are gonna be used for, we are gonna improve our joints and designed joints to be able to install our LiDAR sensors on them.
Okay, outside the cage.
Mm-hmm.
Outside the cage.
Size of the cage?
Outside the cage.
Outside of the cage, yeah.
There's,
Outside the cage?
Obstacle detection, yes, we're gonna.
What's the total payload?
The payload right now is about 1.9 kilograms, but we need more payload because we have not any, with having a camera or sensors, our endurance is gonna reduce, so we are gonna optimize it by the end of the project.
there's one
Yeah.
question there.
What, have you thought about, what kind of lighting you might need for your camera, since it's under?
Yes, that's a good question. For the camera, of course, we need LED lights because the mines in the most of the parts doesn't have any light for us. So the drone needs to provide the lights by itself, and we are going to use the battery for the light, to producing the light by the drone.
So you hang a LiDAR on there, you hang a camera on there, you hang your sensors on there, your battery on there, you got a flight time of 10 minutes.
Yeah, exactly, about 10 minutes, counting about 10 minutes. But our goal is to be more to 10 to 12 minutes, and this is the time that in this age we can do with this drone, because this kind of drone or multi-rotor drones, they have low endurance, with high payload, with the cage, with these sensors, it's gonna be less than the normal multi-rotor, but it has advantages. Multi-rotor drone can hover somewhere and scan, for example, for gas detection is what we need for gas detection sensors. We need our sensor stay for the time, or for ventilation testers, we need something like this. 10 minutes for some mission, for most of the mission works. Yeah.
So you mentioned it, permissibility, I mean, how do you handle that with your electrics?
It's not designed for coal mines. For coal mines, it's a different story. Yeah.
But even all the water, I mean, you talked about there'd be all this dust, and then you showed us 5 slides of nothing but water, which is the reality, but when you're
Yes.
done for-
This prototype is not water resistant, and the mines that we are going to use it is not flooded the mine. But we can use more, when this project is be funded, we can use the waterproof motors and waterproof flight controllers, Raspberry Pi computer, and make it waterproof. It's not a big deal, real big deal.
Okay, guys, no more questions? Nope. Okay, one more.
Yeah, all the sensors and stuff on.
Excuse me?
So what's the total cost?
The total cost up to here is about 1,800. With the sensors, it's gonna be about 2,500 if we use these sensors that we ordered right now.
So what is your guys' plan? Are you gonna try to commercialize this, or is this just a project?
This, the plan is, we have a lot of abandoned mine in New Mexico, so this this is gonna be used with for students that in the future, that they, right now, they gonna collect data for abandoned mine. They cannot go inside. It's really dangerous. They're gonna use this kind of drone or this drone to collect data from that mines. Yeah. And
So are you gonna make this information open source so that other people can build it if it's not gonna be produced by you guys?
Yes, we have already 3 papers in AIAA. They are published, they have UI. You can access the information about what we did with this drone.
All right. Okay, well, thank you.
Thank you.
Questions?
Aren't you giving that to the winner of the ticket?
Yeah. Okay, so our next presentation is, it's from Mark O'Brien. He's not here today, but Rob Johnston is going to be presenting for us today.
Thank you very much. In the words of Monty Python, now for something completely different. Although it does tie in nicely with the idea of being open source. Just very quickly for those that aren't aware who or what the GMG are. The GMG is the Global Mining Guidelines Group, essentially set up with a goal to bring everyone in the mining industry together in order to solve common problems. What I'm going to talk to you about today is basically part of the Artificial Intelligence Working Group, and there are a number of various projects that are underway and have been completed. But I'll not dwell too much on that. The other thing is I'll not dwell too much on how important data is, because I'm assuming if you're all here, you all know about that, and probably you've heard 3 or 4 days worth of all the numbers and how good it is. So let's just save everyone the pain of doing that again. However, what is open data? How is this different from everything else? So in the words of the Open Knowledge Foundation, open data and content can be freely used, modified and shared by anyone for any purpose. You probably know what open data is, but I think that concept of once it's out there in the wild, that's it, it's out there. So I think you have to then make sure that what you're putting out there is right the first time, because once it's gone, you can't pull it back. It's probably worthwhile just looking at what the other types of data are and what the other types of licensing is. You can have a limited open data license, which is really good for academic educational use. It's essentially non-commercial. You could have a subscription or membership-based system where you basically sign up. You probably have to, have some agreeing to some rules, and there may or not be a cost with it. And then I think, the closed, typical NDA type affair is where nobody else gets to use it, in essence. So, what are the perceived issues? Why don't we have more open data? So this came from the Sunlight Foundation, who work in open data. And they basically asked their members, what's the problems? Why aren't we doing this more? And the big one was basically, why bother? Like the mining companies are businesses. If there's no benefit out of it, then just why bother? And then there was technical, how do you do it? People weren't even sure if we wanted to do it, why would we do it? And then obviously the effort and cost is the flip side of the business benefits. If nobody sees the benefit out of it, then why bother? Go to the effort and presumably the cost of releasing this. Can I ask just first of all, is there anybody here that's a lawyer? No? Okay, excellent. Then there's the legal side of it. So we could all agree, engineers, technical management, this is a great idea. And then somebody pipes up and says, let's just put it past legal. And then everyone's heart sinks, because legal are the ones that, obviously they've got, and they do a very important job, because what they're doing is they're protecting the financial integrity of your company, and they're protecting the reputation, which is also very important. So we need to get the legal side on board if we're going to do anything. Privacy, we all know what privacy means in the context of ourselves. So, you know, we don't want our names, we don't want our date of births, our social security number. We don't want that data being out there in the wild. But when we're talking in the context of maybe a mining company, then we're also talking about the privacy of assets. So you probably don't want to have your asset serial numbers out there. You may not even want the name of the asset being out there. So you may just call it asset 1, 2, 3. And then ultimately, there's the privacy of the company. For some data sets, you may be okay to let somebody know it was your data set, but in other cases, you probably don't. You probably want to make it totally anonymous. The one reason I found really, really interesting was accuracy. So people were worried that the data that they were going to give outside the organization may not be accurate. I would be concerned that that data is not accurate inside the organization, because you're using that to run your organization, and you've got big problems if you've got inaccurate data and you run it inside your organization. So what we'll do over the next 5 minutes is basically address these concerns and some things that we can possibly do to overcome them. So first question is why? Why should we do this? Gartner, this is 5 years ago, basically, suggested there were 4 different reasons of why we should do this. But what I'll do is I'll just go through some of them that are specific to mining companies. We're all hearing about, I'm sure everyone's heard in the last 3 days, how machine learning is basically changing our industry. We're using applications such as autonomy, maps, mine planning, optimization, and everyone is telling us that this has got machine learning in it. So the question is, because machine learning needs data in order to have a model, where are they getting the data from? So there's 2 places you can get the data from. One of them is from your competitors. Now, you don't really want to be using a mine planning bit of software that's optimized for your competitors. So you really want to be able to give that data out and make sure that you're part of that as well. The other one is synthetic. So there's been a number, I don't know if you've been in some of the sessions, a number of sessions where the data has been trained on synthetic data sets. And I don't know about your mind, but my mind doesn't follow a Gaussian distribution. It's got lots of noise. It's not real. Sorry, it is real. It's not synthetic. So again, that's just as bad as put it on somebody else's data set. So if we really are going to harness machine learning in our own organizations, we need to make sure that our data is out there so that we can actually get the benefits ourselves. So what other benefits can we get? On the left is a flower. That's an iris. Anyone who's done machine learning academically in a course will recognize that as being part of the iris dataset. It's the most famous dataset that you can use for machine learning. So students are going to learn about flowers. And these students are going to go into your mine. And they're going to know all about flowers. But that's not useful, is it? What might be useful is that they learn about engines, because engines are useful. So where is the data for engines? There isn't any, because I've been looking for it. There's one data set, and I'll show you it later, for oil samples, which is great. Like, wouldn't you prefer the students that are coming in tomorrow to know how to analyze oil samples, engine data, drill and blast, load and haul, anything. Wouldn't you want them to come in and go, I know all about this. Let me take your data and let me do something with it. Or you can get people that come into the pit and look for flowers, which isn't helpful. Researchers as well, let's not forget them. You've got a data set that's out there, researcher picks it up, starts looking into it, and you never know what might happen. They might come back and say, you know, we've transformed the whole of mining, thank you very much, here's our results, on you go and make some more millions. Who's going to say no to that again? So on a more somber note, safety is a common concern to everyone in mining. That is not a commercial differentiation between mining companies. So if there's anything that we can do, any information that we can share that keeps people safe, then I think it's everyone's responsibility to do that. An interesting paper by De Souza last year entitled "Open Data Could Have Helped Us Learn from Another Mining Dam Disaster." Quite a somber title, that. How, you know, will it? I don't know. But the actual, the intent of it really is to save lives, and I think we should all be part of that. So we've covered the why. Let's have a look at the how now. So what data is there? Right? What's the difference between data? Because not all two data sets are the same. So at the very kind of low level, you're going to get the raw unprocessed data. So if you're thinking about a pump, it's just the value. It's the RPM timestamp. Then we'll take that data and we'll do something with it. We'll transform it in some way. We might take noise out. So we're cleaning up it, we're making it more sensible. And then further on down the line, we put more business intuition into it. We analyze it further. So you can see almost in that progression, the raw unprocessed data is actually easier to give out in the sense because it's just raw data. However, it's probably not as useful. That middle line where we've done some cleaning up, it's a nicer data set, it's probably easier. The bottom one, once you start analysing a bit, you've got to be a bit careful because if you're talking about putting people into it or finance into it, then that's something that you really have to start looking at. It's not impossible, but you know, you have to be a bit more careful. Okay, this is what you want to give to your legal guys, because this is what they're worried about. So this is a tool that the University of Western Australia Prognostics Engineering Lab have created. It basically is a questionnaire. It's a, you know, does your data set contain any financial information? Yes, no. And you get a number at the end of it. It's a good tool in that it makes you think about things. It could be made better, more relevant to the mining industry. But if you could take a data set and then go to your management, go to your legal team and say, you know, it's a risk rating of 1.2 out of 10. You've got something where you can actually get some buy-in from them. And it makes them, what you want to do is you want to make their life easy. You want to give them it on a platter and they're just going to tick it and say, yeah, okay, this one looks good. From the point of view of the actual data set itself, I mean, what is a good data set? So we need to make sure it's got plenty of data in it. So lots of rows, but lots of features. The interesting thing is about having features. So features, you know, might be an oil sample, might be, you know, the actual constituents within that oil sample. Now, the interesting thing about that is the more features you have, the more easily identifiable it is against a person, an asset, or a company. The less you have, the less useful it is to actually train on. So there's a bit of a give and take in this. And I was having a conversation with somebody yesterday. I said, well, how do you know? Well, why don't you actually run a model on that data? So you run a model on all of it and see what accuracy you get. And you just keep going down and you see where it begins to tail off. I mean, it's a common thing that machine learning and data scientists will do anyway. But if you can get a 94% accuracy with everything, and a 93.5% accuracy with half of it, then that's good. And if that other half is the bit that you're worried about, you've de-risked it, but not actually taken away the value from the data set. So there's things that we can do in order to help ourselves. It has to be representative of the real world conditions. So we're talking about the pump earlier on. You know, given an hour's worth of pump data, it isn't really useful. A year's worth, okay, it's a lot of data, but that would get some of the real world conditions that might actually help. On the oil samples, for example, there's no point in giving a data set that's got all good samples, because that's useless. Although interestingly, you know, you might have a 90-10 split, and the 90-10 splits maybe you're a bit embarrassed about it. You don't want anyone to know that. But that's okay, because you could balance it and you could give it 50-50. And you could say, I've balanced it for you. So there are things we can do to make the data sets good quality and to take the risk away from ourselves. And of course, we've talked about de-identifying everything. But what goes well together with an actual good data set is good metadata. So you need to describe that data set. Because once it's out there, somebody's going to look at it and it's going to say, well, what is this? You know, what is column 42? The deep learning attitude is, it doesn't matter. You just throw the whole lot into deep learning and it will just sort things out for you. However, that's not always helpful for a variety of different reasons. So explaining what the data is, explaining roughly where it came from, you know, what kind of conditions, that's important to go with it so that somebody has an idea of what they're doing. So let's just a very quick example, and I'll use the UWA again. So they collected, I think there's about 7 or 8 data samples. They were looking at prognostics. And so they've got a website, they've taken the data sets up there. You can choose a data set. It's got nice information. It's got what's the details in it, where it came from, what papers have been written about it. Click download, and you've got your data. So this is the type of things that we're talking about. This is the oil sample data that I was talking about. And so you can now use that, and you can now work on that under the terms of whatever and the terms for this one is non-commercial. But you've got that now. You've got access to that. So I've talked a lot about data, but not a lot about GMG. And this is where we start to tie it all together. So what is GMG doing about this? Why are we doing this at all? So the way that GMG works is there's basically an open question. You might even have filled out some of the questionnaires last year. What's the most important thing to the mining industry in this context of AI? And data sets was one of them. You know, the lack of good data in mining is a problem. Other industries don't have such a big problem as we do, but there isn't anything out there for people to use. So that was identified as an issue. And when we're looking at it, we thought, well, there's 3 major things that we can do here. The first one is, what is out there? Let's try and find out everything that's there for mining, because there's bits and pieces all over the place. Let's just try and pull it together and just even reference it. We don't actually have to post it or do anything, but let's just see what the current situation is. And then when we talked about a lot of the issues and a lot of the whys and the hows, well, they're all still questions. There's nothing solid there. So what we can do is maybe tie that all together. We need to have some guidelines where if people want to do this, they've got something that they can actually go to their management and go to their legal departments and have a recipe for how can we convince ourselves that this is a good idea. And putting the benefits out there is important, because nobody's going to do this if it's going to cost them money and effort and isn't going to have any benefit. So we need to be able to have something which can be mining universal that we can actually use within our own organizations. And not only that, we also need to have some guidelines as to what do we expect from a data set? What makes a good data set? And I think that's important, that we bring everybody together. We learn from other industries as well, And we bring that knowledge together so that we can actually have a recipe for doing this and doing this well. And then finally, once we've got this, let's go out, let's go and try and get some data. Let's try and actually walk the walk. The talk's easy, but it's actually doing it is actually going to be the hard bit. But that's going to be where we get the benefit, is actually convincing people that the data is important. So, thank you very much. The QR code there is for the GMG site, so take a photograph, go on, get more information. So, yeah, thank you.
We have a couple minutes for questions.
So I'd like your thoughts about the difference
sorry.
between the data
I'll put it again.
and the structure of data, and who owns which. So in other words, if we have an open structure for information, but the data is exclusive to a company, wouldn't that be a better way of approaching the problem?
That's, I think, a different problem. Are you talking about interoperability?
Well, it's interoperability, but, when we probably look at AI structures, there's probably going to be just a couple of different structures for that. But nobody's kind of come forth and said, well, here's a good structure for this. But if somebody owns that, it makes it impossible for anybody else to use it. So that would be a fantastic way of approaching the problem. Because of the content, people do tend to still be very protective of that content. The content or the sandwich, if you take the analogy, instead of the container for the sandwich, that can be theirs, but the structure can be ours.
So, I think we need both. And I think that's why, that's why we need to make it easy for both. There's some data which we don't have to open the floodgates and give everything out. So that's what governments are doing just now. Because governments, they have no commercial advantage over keeping that data. They want to do that. But what we can do is we can be selective in giving stuff out. So I understand what you're saying in that we want to keep, and we do want to keep, like anything that's of competitive and commercial value, there's no way you're going to give that away. But a failure rate on a machine, can you give that away? Would you be happy to give that information out? So I think what we do is there is a spectrum, and I think you made a very good point. There's a spectrum where for every different company, for every different person, there's a slider for where you feel comfortable that this stuff is okay and this stuff isn't. Well, even if we did the slider here, this stuff down here, that's still more than what we've got. So let's just focus, let's focus on the stuff that everyone's happy with. It's one company may say, I'll just do oil samples, and another company may say, well, I'm happy to give you some of my drill samples. We don't have to go out and get everybody to give us all the same data. If we can get people to give us some data, then that's a huge start as it is.
If these companies saw that there was no value in, if these companies saw that there was no value in giving out this data, why haven't they already done it? I mean, what benefits haven't they gotten already by allowing just open source data? Because there has to be a reason why they're keeping it proprietary, at least from a geology perspective, and being in the United States, we don't give out our data because we can sell that data to the next, whoever comes in and works the project next.
So and that's your point, and I think that comes to your point as well. That's got commercial value. So you're dead right, you're not going to give away commercial value.
So what data doesn't have commercial value, I guess?
But did you miss the part about the lawyers? I mean, it's not just value, but it's negative value as well, it's risk. exposure as well. You might not have any really value on the books, but letting data get out that you somehow then get sued for who knows what.
So, I mean, in what you're talking about, you know, you have to wait until there's, you know, exhausted demand, and it's not important anymore. You know, if you're not at that point, then you're not going to give it away. But again, to come back to, you know, the instances that we've talked about, the smaller and more localized it is, rather than the larger, you know, corporate size, the less risk there is. So what you're talking about is, you're talking about the big picture. You're talking about, you know, millions and millions of dollars worth. But if you're talking about, you know, machine, the channels of a machine, then, you know, that's not got, it's got very little risk. I mean, it's one machine. It's the asset health of that machine. Where's the risk in that? So, you know, I think, and I think those two questions are really at the heart, I think, of why we don't have more data out there, because what we're doing is we're concentrating on the things that scare us the most. But if you open a data set, it doesn't mean you've opened everything to the world. So let's just go all the way down to this side of it, and let's pick the things that are easy, and then let's try and get that stuff out. Because the thing is, when you look at the applications that this data is used for, nobody's taking that application, and I'm sure somebody would love your data if you made it open, but you know, nobody's needing that data for their autonomy, for their mine planning. They don't need that data. What they're wanting is this data down here. And we could probably give that data without actually harming our organisation in any way whatsoever. But it is benefiting everyone. I mean, the saying about, you know, a rising tide lifts all boats, that's what we're talking about here. What we're talking about is a whole industry getting better.
I think miners see it as more of a zero-sum game than other industries. And if I help him, it's going to hurt me somehow. I have an advantage as a miner because a commodity price is different than a consumer product price. Okay? You want to be that low-cost producer because that attracts capital.
I agree with the first part. I think that is the state of play just now. I don't actually necessarily think it's true, which you're probably of the same mind.
I'm sure that's quite
yeah.
Absolutely.
But I think again, you know, we choose the data sets which really, you know, attract no risk or very, very, very little risk, and then we make it easy. We make our own organisations comfortable with this whole idea for exactly that reason. At the moment, you just go to a lawyer and they'll say no, and you're like, I haven't started talking yet. So we need to make them really happy with my lawyer being happy. I'm going to make a push check. We need to make them at least, you know, comfortable with what's happening here. And there are benefits. And I think what we haven't done is we haven't actually done a good job of selling the benefits. It's all about benefit realization. I mean, that's what we're in business for. And if we're getting some benefit out of this, then yeah, you know, why not do it?
So you said you did a survey of sorts of what data is available.
So what, oh yeah, sorry, yeah.
Is that in the paper? Is that on the website?
So we're collating it at the moment with, and we will.
Because on the other hand, there's all this stuff available, then you might have an idea of what you'd like to have available. And that's another good starting point.
It's interesting you put one hand up with 5 fingers, it's available. Yeah, because I actually think it's 6, but close. There isn't a lot.
I got some flour data I can give you.
Excellent. More flavors.
Okay.